Alright folks, so first things first course is essentially what we're going to be doing is a review of mechanics. This course is very much so a follow-on of your statics course. Essentially the first step of any of the problems we'll be doing is doing a static analysis of the component in question. So essentially we're using 231 as a building block and stepping off from there. So if you didn't do too well last year, I highly suggest you brush up in the meantime. But anyways, so we'll do a few quick examples here. But as for the steps, you need to find your equilibrium. So you know how it is. Draw your free body diagram, label your reactions, add your distributed loads. Usually the easiest way to do things is break your forces up into components that are parallel with the axes in question, and then go ahead and add those up. Add up your forces, add up your moments, solve your unknowns based upon an equilibrium condition. So, start with this problem right here. So what I'm actually going to do is take that problem and I am going to cut and paste it here into OneNote. We'll be kind of working from there. So we got this problem here, restating the problem that we're going for. Again, we're trying to find the internal loads at point D. The assumption here is that the reaction at the supports are vertical. Again, that seems like a reasonable reasonable assumption. There's no horizontal forces that would be generated in this other than reactions at the supports. So as a result, anything that would be generated would be negligible. You're probably going to get a little bit kind of as the beam starts to bend down a little bit. It's going to, even if it's not welded or bolted onto those other beams there, it's going to have a tendency to kind of want to slide in a little bit. So that's going to cause some sort of reaction force at each end, but those are going to be equal to one another and relatively small. So we'll start off here by sketching a free body diagram. So we got our beam. We got a reaction force A. I'm not going to bother labeling it FAY because of that assumption that we talked about earlier. But obviously you want to be differentiating between your X and Y components of various reactions otherwise. So we got that. Before we go any further, before we start delving into exactly what's happening there at D, we need to figure out what's happening overall. So let's figure out what the resultant of this distributed load here is. We know that's a nice triangular shape there. So we calculate the resultant there by basically getting the area of that triangle. So we got a 4 kilonewton per meter distribution kind of at the top, and it tapers down to nothing at the sides there. So that's going to be 4 kilonewton. That is a terrible looking N. Kilonewton per meter. And then times the width here. So that's 6 meters total. And then again, we're working with a triangle, so it's half of that. Width times base divided by 2. So we got our 6 meters, which cancels out with the kilonewtons per meter. 4 divided by 2, 2, 6. That leaves us with 12 kilonewtons. So that's the resultant. Where's it going to be acting? Again, it's a triangle. We know that the centroid of a triangle is located 1/3 of the way up the triangle from the base, or 2/3 from the tip. So we can just place that here. Got a 12 kilonewton force, and that is located 2 meters away from this support on this end. So let's delve into our equilibrium equations. So some of the forces in the y direction are going to be equal to 0, since this is an equilibrium problem. Therefore, Fa plus Fb minus 12 kilonewtons is equal to 0. So basically that allows us to solve for each of these forces in terms of the other one. So we can go ahead and do that. Let's do Fb. Fb is going to be equal to 12 kilonewtons minus Fa. So we need a bit more information for this. So let's take a moment about a point. Again, you can pick any point along here and it'll still work. Generally speaking, you're going to want to pick one of the points where the forces are acting through, because that allows you to ignore one of them in the calculations, because the distance from that point to the point the distance from where that force is applied to where you're taking the moment about is 0. So it cancels out that force in the moment reaction. So let's take a point about let's take the moments about Fa. Sorry, about A, not Fa. So the sum of the moments at A is equal to, so again, the Fa1 cancels out, so we're left with, I'll start on this end, we got Fb B times the distance between there and there, that was 6 meters. Now, then we also have, so we've got our 12 kilonewtons here. The 12 kilonewtons is acting in the opposite direction. So that's a negative 12 kilonewtons. So plus negative 12 kilonewtons, or you can just throw a minus sign in there to begin with if you really want. Crossed with the distance here, that's 2 meters. And all that is equal to 0, since we are solving for an equilibrium equation. So that relatively simple. That allows us to solve for Fb. So Fb, and move this stuff over to the other side and then divide by 6 meters. That's going to be 12 kilonewtons times 2 meters divided by 6 meters. Alright, well, we can cancel the 6 and the 12 out. It goes to 2. Meters and meters cancels out. That gives us 4 kilonewtons at Fb. So, we've got Fb. We can solve for Fa as well. So now that we have, I guess I probably should, yeah. probably should have taken the moment to put another one, since now we gotta rearrange stuff around a little bit. But to solve for FA, we just use this equation here. I'm going to rearrange it a bit. So FA is going to be equal to 12 kilonewtons minus FB, which is equal to 8 kilonewtons. So now that we have kind of our supports, what we're really worried about here is the internal reaction at this point D. So what we're going to have to do is we're basically going to have to take a slice of that section there and then analyze it. I'm going to cheat a little bit. I'm going to actually switch over to here and kind of take a screenshot of that there, and then copy and paste it. And let's stretch that out a little bit, so we can, when we draw our free body diagram, it kind of looks a bit bigger. So we still have a beam. It's just a section of a beam. So we need to kind of figure out what the distribution here is. We know up here, this is a nice triangle, starts at 4 kilonewtons per meter up here, drops down to 0 over here. So at this point here, well, that's it's a 6-meter beam, and we're kind of and we're 1.5 meters away from this end. That's 25% of the way. So at this point, we're 25% of the way to growing up to 4 kilonewton meters. So that value there is going to be 1 kilonewtons per meter. Right there. So based upon that, again, we are going to have a resultant force from that distributed load. Again, it still will be placed 2/3 of the way from the tip. So there's going to be 1 meter between here and here, 0.5 between here and here. We have our FB, which we know to be 4 kilonewtons, and we know that's the only reaction at B. And next things next. We also have, we're going to have a shear load. So basically, when we take a slice here, what we're doing is we need to find the internal forces. So basically, when you're pushing down like this, what's going to happen is that the rest of this beam is going to be pushing down on that face there. So there's going to be a downward force that is going to be applied on that face. We'll call that V, because we use V for shear, because that's a shear load. As well, there is going to be a moment that is generated as well. We know that there's going to be we'll go into more detail, but about the relationship between moments and shear and direct shear later. But there is going to be one at that point. So basically, there's in addition to the shear load, there's going to be some sort of weird distribution of axial load that cancels out on this face. There's not going to be any net axial load, but there's going to be a distribution of positive and negative at various different points that causes a moment. So I'm just gonna assume at this point that is going to be acting in that direction. We'll call that moment D. So, what do we need to do in order to find out what those forces or moments are? Again, we're just taking more equilibrium, solving for the equilibrium equations. So let's just go over here. And we are going to basically be taking the sum of the forces in the y direction. Those are going to be equal to 0. So let's just add them all up. 0 is equal to, we got this 4 kilonewtons here. Kilonewtons plus, we got the resultant here. I guess we need to solve for that first. It kind of slipped my mind. So the magnitude of that is going to be 1 kilonewton per meter times 1.5 meters. So height times the width. And then again divided by 2 because it's a triangle. So basically 1.5 kilonewton meters divided by 2, that gives us 0.75 kilonewton meters. Oh, sorry. Not kilonewton meters. Our meters cancel out. Just kilonewtons. 0.75 kilonewtons. But, actually, wait, no. Screwed up there because it's acting in a different direction, right? So that is a downward force, so we treat downward forces as negative. So we're subtracting that. And then we also have this shear force here, so minus V. And then just solving for V gives us 4 kilonewtons minus 0.75 kilonewtons, 3.25 kilonewtons. So we've got our internal shear at that point. Not too complicated. Now we just need to figure out what this internal moment is. So in order to do that, let's go ahead and take a moment about B here. So we're gonna the sum of the moments at B is equal to 0. So FB doesn't come into play there because displacement 0. So let's just add the terms up that do come into play. So we've got our P here. So again, that is a negative P, negative 0.75 kilonewtons times here, again, you need to keep your sign conventions in mind, times a negative 1 meter, because the displacement vector here, from here to here, is negative, because actually I did forget to define our sign convention, but here it is. The x is positive in this direction, y is positive in that direction. So the vector from here to here is a negative 1 meter. So that'll be negative 1 meter. And then plus, we also got our V here. So again, that is another negative 3.75 kilonewtons times, that's 1.5 meters, but again, a negative 1.5 meters. Plus our MD. So you'll note that I kind of put MD here in the going in this direction because I'm pretty sure that's the direction it'll be. But again, due to the fact that when you're doing your because we're working in the right-hand coordinate system here, the MD is a clockwise, is here noted as a clockwise moment, so it'll be a negative as well, as opposed to these two moments here, which end up being positive because they are because they're forcing this thing to move in a negative, in a counterclockwise direction. So that'll be minus MD. So that, let's do the calculations to collapse these down. So that one's easy enough, 0.75 kilonewton meters, plus, for that one we're going to have to bust out the calculator. 3.75 times 1.5, again negative times negative cancels out, 4.875 minus MD. That's equal to 0. So it lets us solve for MD just by adding MD to both sides. MD is going to be equal to, take that previous value, add the 0.75, that gives us 5.625 kilonewton meters. So again, that's kind of in that direction. Now, the thing is, we've solved for these forces, we've solved for V, and we've solved for MD. The thing that you do want to keep in mind is what we discussed previously with regards to sign conventions. So when we're looking at our sign conventions for beams, again, we need to keep these sign conventions in mind because you can't just say the force is going up or the force is going down, so that's a positive or negative internal shear, because then it depends on what side of the cut you took it on. So, that's, somewhat arbitrary. So in this terms, internal shear is positive if it would cause a clockwise rotation of the element. So going back here, we got V here, pushing downwards on this side. So that would actually be causing a counterclockwise rotation of the element. So based upon those definitions, the shear force here is going to be negative. Whereas the internal moment here is positive if it bends in such a manner that it kind of forms a little smiley face, or it forms a cup, so that it's if it's if you take something flexible and you apply rotation this way on this end while doing holding this end, it's going to cause it to kind of bend like that, right? So that forms a space here where you could hold some water, or looks a bit like a smiley face. So in that instance, MD there, that would be a positive internal moment, whereas this shear here, that one's going to be negative. One other thing I should probably mention also is we haven't discussed significant figures here, but I mean, to be frank, we were told 4 kilonewtons per meter. I think a lot of the times with these problem sets, they kind of assume, at least the answer that they give in the textbook assumes far more precision than what they actually specify. If they'd said 4.000 kilonewton meters. Now we could justify going to 4 significant digits, but realistically, we really should be rounding these down. I'd say, the most precise that we could reasonably justify is that the internal shear is 3.3 kilonewtons, the negative 3.3, and the M is a positive 5.6 kilonewton meters. So let's have a look at the next one on our agenda. I'll go with this one here. Again, I am just going to snapshot it, and then I'll start a new page here in OneNote. So we've got a shaft supported at its various ends by by 2 bearings, and subjected to various forces. So they want to figure out what the internal loadings are on this cross section at C. That's for this question. I'm pretty sure that they ask about D for another question. So this force is acting in the negative Z direction, so pulling downward. These 2 forces are acting in the positive Y direction, so that is pulling kind of towards us a bit, kind of depending how you view this orientation. And so we are, first things first, obviously we need to kind of state what we're looking for. And the assumption so basically, I should move that down a bit because my face is covering it. So restating our question there, we are assuming that the bearings again are only acting. They don't have any axial forces, so they're not thrust bearings. That have been said. Again, there's no other external loads being applied here that have any axial components to them. There's nothing pushing or pulling in the X direction. So the assumption here that the journal bearings are only exerting Y and Z components is, probably not completely accurate, but fairly reasonable. So the best way to go about this, free body diagrams? Diagrams? Yes, absolutely. Because we're gonna, we need to be solving for the kind of 2 different orientations of the forces that are being applied here. So we're gonna be wanting to draw free body diagrams that are in different orientations. So let's start with a drawing of the shaft, and let's put that in the X and Z plane here. So any of the forces in the Y direction, essentially at this point we're going to be ignoring them because they're coming in and out of the page. So when we do our kind of force, our equilibrium or our moments, they don't come into play. So based upon that, we are going to have a reaction force in the Z direction at B. And we're also going to have a reaction force in the Z direction at A. And then we are going to get the combined value of these two 400 Newton forces that are being applied at this point here on this pulley. So that's 800 newtons. 300 millimeters away from A. And let's see, that is a combined 400 plus another 300, so 700, 900, 1,100 millimeters from where the B journal bearing is. We could place these other two bearings on here. I guess I'll just sketch them on here. But again, they're not all that important for this diagram, since there aren't any forces that are acting in these planes that we're concerned about. So now to start off, let's just do the sum of the forces in the Z direction is equal to 0. So that is going to be equal to negative 800 newtons plus FZA plus FZB. Next up, all right, next thing we need to know is basically the sum of the moments. Let's say the sum of the moments at point A. That's equal to 0. So that one, again, we got minus 800 newtons times the distance between here and here. Millimeters plus FZB times total distance here is 1400 millimeters. So that one's a positive force, and the displacement is also positive. So that just allows us to solve for FZB. That one's going to be equal to, let's see, it's going to be equal to 800 newtons times 300 millimeters divided by 1400 millimeters. Millimeters cancel out. That gives us an FZB of 141.4 newtons. Then we can basically solve for FZA as well. So FZA is going to be a lot larger than FZB, but based upon this equation, that's just going to be 800 newtons minus 141.4 newtons. Which gives us 628.6 newtons. Okay, so we got all our unknowns on that particular graph. That particular free body diagram. So next step, let's change the orientation. let's instead do a graph that has an orientation of x and y. So again, we've got our reaction forces here. FYA. Actually, just 1 second here. One thing to keep in mind, the positive direction of y is going out here. So these forces here that are being applied are going to be positive forces in the y direction, which means that the two reactions designed to oppose those are both going to be negative. So I can actually just go ahead and throw that on there. Obviously, by the time we got around to solving it, it would have, when we solved for it, it would have had a negative sign. But we can just, skip it. We can just annotate things in the direction we expect them to be in the first place. FYA, FYB, and then we have these two pulleys here. Okay, so this one is, let's see, that's 400 plus, that one's basically just straight in the center. So that's 700 millimeters from A and from B. So stick that one. So that is a positive force in the y direction. Its magnitude, 200 newtons plus 200 newtons, 400 newtons. And then we have this other one here, 300 millimeters to the side, and that one is 80 newtons times 2. So 160 newtons. So there is 400 millimeters between here and here. And there is 700 millimeters between here and here. So, let's, how about we start, okay, so the point that we're looking for, the point of importance here is point C. So let's solve for the reaction force over in A. So we can do that by the easiest way to do that is just by taking a moment about point B there, because then B disappears while we're solving for the moment. The sum of the moment at B is going to be equal to 0, which is equal to, so what do we got here? We have, okay, so FYA is going to be negative. And it has, and the displacement vector from here to here is also negative, so the resultant moment is negative. So that vector there, that displacement is 1400 millimeters. Next one we've got the 400 newtons, so plus 400 newtons times this displacement vector from here to here, again negative 700 millimeters. And then similarly for this other force here, 160 newtons times negative 400 millimeters. So, based upon that, we can solve relatively easily for FYA. So, let's just take these terms, move them over to the other side, solve for them. So we've got 400 newtons times 700 millimeters. And I'm just going to put in meters and Newton meters instead in order to keep the numbers a bit lower. (280 Newton meters) plus 64 Newton meters is equal to negative FYA. Oh, I forgot to actually put the negative sign on that, so times the negative, do that now. So, okay, we'll take the 64, add it to the 280, that gives us 344, then divide that by the 1.4 meters, and that gives us an FYA of 245.7 newtons. So, you know what? We've got FYA, and we're trying to find the internal force at the cross-section C. You don't really need to know what's going on at B, right? We needed to figure out what was going on at B in order to find out what was going on at A, but at the end of the day, you know, that's not really necessary for the problem and that they asked us to solve. Don't necessarily need to be doing any extra work. So what we can do is we can just draw a set of free body diagrams for just that little section there. So let's do this. We'll make it a bit larger. So we got, okay, so 500 millimeters between A and C, another 300 millimeters between A and the pulley system here. So put that pulley system right about there. So A, C. Let's make this one the XY plane. So got FYA that we just solved for right there. For the component of the Y, for the Y components of the force on the shaft, we got, we actually don't have anything there, do we? That one's just acting in the Z component. So we got that force, which tells me that we are going to need to have some sort of other force counteracting that force there. So let's call that, that's a shear force, we'll call it V, let's call it Vy, since we're also going to have a Z component to our shear that we need to take into account later. So in addition to the reaction shear force V, we're also going to need to have a moment reaction there. Otherwise, this thing's going to start spinning uncontrollably. So we'll add that there. Oh, there's another is. Let's see, let's call that. So this is a moment in the Z direction at C. So now that's all the reactions we've got. The journal bearing itself doesn't have any moment reaction going on. It's just preventing a lateral movement. It's not preventing flexion of the shaft in question. So we can just sum up our forces in the y direction. That's equal to 0. Well, what forces do we have here? That gives us 245.7 newtons minus Vy is equal to 0. And guess what? That's pretty easy to solve for, right? Okay. As for our other unknown, let's go ahead and just take a moment about point A here. Sum of the mz's at A is equal to 0. So then we've got a negative force times a positive displacement. What's the distance there? Again, this total distance across that that section to C. It's going to be 500 millimeters. Yeah, I'll label that on the free body diagram while we're at it. And then plus our mz, our moment reaction in the z direction at C. That's all equal to 0. So just solving for our unknown there, mzc is going to be equal to, oh, I forgot to throw a unit in there, that's a Newton. So combine the two there, 245.7 times, let's stick this in meters instead, so we got a smaller number we're dealing with. That's 122.9 Newton meters. Okay, now got a reaction there in the Z direction, or well, about the Z axis, I guess is another way to look at that. So that'll be our free body diagram in the XY plane. We're also going to need to have a free body diagram of the same space on the XZ plane. So again, kind of the same idea for reactions at the sides. We know that the reaction for FZA is 628.6 newtons. And that's the only reaction that's going on at point A there. Got point C here. Better distances going here as well. So again, scrolling up, so it's 300 millimeters between A and the pulley, and then another 200 millimeters between pulley and our point of interest C there. Okay, so we know that the reaction at A was in the positive Z direction. We know that the forces being applied at the pulley here are in the negative Z direction, and that's going to be a total of 800 newtons. And then we're going to have another shear reaction here. We're going to call that VZ. So that's all our force reactions. We're also going to have a moment reaction that's going on there too. So let's go ahead and throw that on there. I'll call it MY. I'll clean that up a little bit better. MYC, so the moment about the y-axis at C. And then denoted here as a positive moment, counterclockwise. Again, I'm not sure if it will be, unlike the other one, isn't quite as easy to eyeball, but you know, math will work out at the end. So, first things first, easiest thing to do here would be to figure out what the value of our VZ is. So we do that by taking the sum of the forces in the Z direction, that's equal to 0, which is equal to Fz plus 628.6 minus, it's a terrible looking minus sign, minus 800 newtons. Oh, that's a newton too. Alright, so simple enough to solve for VZ there. It's going to be 800 newtons minus 628.6 newtons, which my handy dandy calculator tells me it's 171.4. Okay, so next things next, let's go ahead and take a moment about one point here. I'm going to pick here just so that all the displacement vectors are positive. So I'll pick point A. So the sum of the moments but the y-axis at A is equal to 0. So that means that 0 is going to be equal to negative 800 newtons times 300 millimeters plus our 171.4 newtons times 500, terrible looking 5. No, you guys can't see that anyway, so why is it going off the screen? Just 1 second. Sorry about that. I'm not sure what caused that to kind of go off there. Anyhow, so and then also plus our reaction MYC here. So simple enough to solve for that. MYC is going to be equal to 800 newtons times 300 millimeters minus 171.4 newtons times 500 millimeters. And I'm just going to divide by 1,000 in order to convert that to Newton meters instead. So I went ahead and collected those together off camera. And so we've got Vy is that, Vz is that, Mzc is that, MYC is that. Now the thing to keep in mind is that those are the values based upon the orientation of the arrows that I threw on here in the first place. Now if we want to report the internal loading, we do need to keep in mind that we are still working with the definitions that were provided for the sign conventions that we talked about earlier. So for the shear, if we take a tiny little slice off the end of this thing here, and if that tiny little slice would cause that little, if the internal shear caused that tiny little slice to rotate in a clockwise direction, and I'm reversing the directionality of my finger here so that you guys can see it. From my perspective, it's the opposite. That will be a positive shear. So for this particular one here, we have the upward shear being directed on the right side of the slice, which would, and then obviously on the other side of the slice it'd be downwards to counteract that. That's going to cause it to try to rotate counterclockwise. So Vz is going to be a negative shear. Vy, on the other hand, well, it's the opposite sign, so I think it's fairly obvious that that's the opposite sense of this one, so that one stays positive. The MYC and the MZC, those are both going in the same direction. And basically, if we just we say took a slice right here and then zoomed in a lot, we have our M here, and then obviously on the other side of that bar we have a counter of that little slice, we'd have a counteracting one, and that would be a orientation such that it would cause this bar to form a nice happy face. Happy is good. That makes it a positive moment. So both of these things stay as positive moments based upon the sign conventions that we talked about earlier. If any of you are following along in the textbook and wondering why the answer that they gave is different than that, the problem here is that when the textbook introduced the sign conventions that we talked about, they did so in chapters 4, 6, and I believe 9. Different spots for the different conventions. So unfortunately, and these questions are from chapter 1. So basically, they're not using the sign conventions at this point because they didn't talk about them yet. So that's about it for this question. Here we have our internal loads at those points. I suppose I should probably mention we do also have a normal load, which is 0 newtons, and we have a torque, which is equal to 0 newton meters. I guess it certainly doesn't hurt to mention those. If you're doing an assignment or a quiz or what have you, and you leave it out, I'm probably not going to be too upset.